Some buses don't want to open the door now when the driver takes the decision by himself that the bus is full enough. Okay, so how is everyone doing? Good? Let's continue our class. So we have a nice week ahead of us. So this is our real analysis 2020. Let's see, and this is lecture number 9. I want to finish the discussion today on LP spaces, perhaps talk a little bit about Jensen's inequality, and a little bit about Hilbert spaces. Let's see how far I can go. Okay, so last class, we started studying, so this is just a brief review. We start discussing the LP classes of functions, right? So LP, for certain set omega with a sigma algebra and a measure, would be the classes of functions f measurable such that this so-called LP norm was less than infinity. Okay? And the LP norm was the integral of absolute value of f to the p d mu, the 1 over p, when 1 was less than p less than infinity, and was what we call this L infinity norm was the essential supremum of f. Okay? And recall that we are identifying functions in these spaces. F is going to be equal to g. We are identifying, no, this is just identifying functions that are equal almost everywhere, okay, with respect to the measure mu. So we identify functions that are equal almost everywhere, for we don't distinguish them anymore. And then these become, well, these are vector spaces. If you add up two functions with finite LP norm, the sum has also finite LP norm. You can multiply by your scalars. You can be working with real valued or complex valued functions here. If you multiply by a scalar, the scalar comes out. And this is actually a norm because we have proved this triangle inequality here, right? So this is less than or equal than Fp plus Gp. So this is the triangle inequality, sometimes known as Minkowski's inequality. So in fact, this thing here is, well, from your space LP to 0 infinity open is a norm. You have to make this identification of functions almost everywhere to say that the LP norm of a function is 0 if and only if the function is 0 in this sense. So you have a vector space, you have a norm, then you have a normed vector space. And the theorem that we ended up proving last class was that this is actually LP is a Banach space. Meaning that it's a complete normed vector space. A complete means that every Cauchy sequence converges to an element of the space, right? And if you recall, the main elements of the proof here would be if you start with a sequence Fn, Cauchy, a Cauchy sequence in the space, the idea was to use the definition of the Cauchy sequence to choose a subsequence. You would choose a subsequence that gets very close. We call this sequence GK. We can choose a subsequence such that GK plus 1 minus GK in the LP norm was less than 1 over 2 to the K. Okay? And the idea was to construct our limiting function f, f of x as just what would be the limiting functions of these g's. So we just wrote g1 of x plus the sum of gk plus 1 minus gk. Okay? And here this goes from 1 to infinity. Well, of course, the partial sums of these things, if you just sum up to n, this is actually the limit of these functions gn of x, as n goes to infinity. Okay? But you prove that this was at least a well-defined function, to prove that this sum is absolutely convergent for almost all points x. So I'm actually defining a function here, not saying that it's infinity. We had to take a step before and actually consider this function with absolute values here. So we had actually to consider first the one with absolute values here, and we proved that this function with the absolute values was, in fact, in LP. This is a non-negative function, so by monotone convergence and applying the triangle inequality, we proved that this is in LP. Therefore, the sum is finite almost everywhere. Therefore, if you take off the modulus, it's finite almost everywhere, too, because if a sequence is absolutely convergent, it's convergent without absolute value. Then this defines a function, and then we ended up proving that this Fn actually converges to this f in the LP norm. Okay? This was what we ended up proving. So there is a function f that lies in LP such that your original Cauchy sequence, Fn, converges to f in the norm of the space. All right? I just wanted to highlight that there's a corollary of this. The corollary of this, of the proof of the result, we get the following thing. So if Fn is a sequence that converges to f in LP, so if you have a sequence that converges to f in the LP norm, meaning that this means that f minus Fn, the LP norm goes to 0, okay? This is what it means to converge in LP. Then there is a subsequence that converges, subsequence, let's say f and k, such that f and k converges to this f pointwise almost everywhere. So every time you have a convergent sequence in LP, you can extract a subsequence that converges to your limiting function pointwise almost everywhere. This is here in the proof. This subsequence is actually this Gn. Gn converges pointwise to our f almost everywhere. Okay? And this is actually, think about why this is actually the best that you can do. You can have a sequence of functions Fn converging to f. Can you ask yourself, oh, if Fn converges to f in LP, do I have that Fn converges to f pointwise almost everywhere? The answer is no. Just up to a subsequence, but the whole sequence doesn't need to have a limit, almost everywhere. Think about it, why? Okay, another important piece of information that we proved was Holder's inequality. Right? That says that if you have exponents p, q, and r, less than or equal, bigger or equal than 1 and less than or equal than infinity, then the norm of the product fg in the LR loses to f in LP, g in LQ. So the product of these two norms controls this other norm. And I sent you as an exercise this week to study the cases of equality in Holder's inequality and in Minkowski's inequalities, okay? So you check out those exercises. And then we concluded last class with a little bit of a discussion on the duality properties. Okay? And the duality properties of that you could express the norm as a sup if you multiply by the functions in the dual space. So remember, whenever you have an exponent p, this exponent that we call p prime is the one such that 1 over p plus 1 over p prime is equal to 1. These are called conjugate exponents or dual exponents, okay? So these are dual or sometimes called conjugate exponents. The idea is that, well, if you want to find the LP norm of a function f, you could go through the definition, that's fine. But sometimes a simpler way would be, well, you just take a product of f by some functions g, forget about the modulus, forget about the integrating to the p, just take f times g in your omega, and you take the supremum over these quantities over all g's in LP prime, g's in the norm p prime less than or equal than 1. Okay? And this is what you get. Okay, so it's this supremum. And I commented to you that if 1 is less than or equal than p less than infinity, this supremum is actually attained. Okay, so this supremum, this sup, is attained. Meaning that you can actually find a function g in LP prime such that this integral is equal to this LP norm. So the supremum is attained, therefore it's a maximum. This is not true. This is not the case. Not the case if p is equal to infinity. Or maybe the other way around. Let me think about it for a little bit. What did I write to you? No. Did I get this right? Supremum is attained. I claim to you that this is not the case, this may not be the case, if p is equal to infinity. Well, if p is equal to 1, you always have oh, no. I think I made a mistake here. I might have made a mistake here. Sup in LP prime. So let's think about what happens if p is equal to 1. G should be essentially bounded, right? But can you actually construct an essentially bounded function such that the integral of fg is equal to the L1 norm of f? G is just the signum of f. You're right. Okay, so then I might be okay. So what about if p is equal to infinity? If p is equal to infinity, so you have f being an essentially bounded function, can you find a g in L1 such that the integral of f times g is going to be the norm of f, the infinity norm of f? Yes. But what would be an example? So if you just take, for example, the function f of x, so an example when p is equal to infinity. If you just take an example of f of x being identically equal to 1, what happens with this function? This is certainly a function in L infinity. It's identically equal to 1. Does this Can you find a G in L1 with norm L1 less than or equal than 1? This is what I want. Can I find a G in L1 so the infinity norm of F, let's think about first this example. So the infinity norm of F, oh no, this would be okay. So this, when you try to work with, when you try to construct counterexamples, the examples where you have things flat at infinity would be the first one to do. Let's see, this is not going to work because you can just take the function g, any function g positive here with the integral of g being 1 would actually be an equality here. That's fine. So this doesn't break. You can really find a g with integral 1 such that the integral of f times g is going to be equal to 1 is equal to the L infinity norm of f. So this is a bad example. But let's take a look at the second example. So I think this is what's going to work. So now take a function f that has the L infinity norm, but it attains at a little peak. So just take a function like this. Okay? Just take f to be this function here. So really, let's say it's 1, minus 1, and 1. So the L infinity norm of this function is 1. But think about, if you take any function g that is integrable with norm 1, when you hit this with f times g, this will be always less than 1, because the mass of g, the function g, cannot be concentrated just at the origin. The function g, being an integrable function, will have to have mass outside this set of measures 0, but outside this set of measures 0, when you multiply by f is going to be less than 1 in absolute value. Okay? So think about it. This is a good example to show that this thing here, when p is infinity, this L infinity norm, there won't be a g in L1 such that this is actually equal to the L infinity norm of f. Okay, so think about it. All right, guys and girls, this is where we stood in the last class. Let me continue our discussion. And so we will see, I want to show to you, maybe by the end of this week, that this duality statement goes a little bit beyond this, okay? So I want to perhaps take the time to properly define what's a dual space of a Banach space, okay? And we are going to prove that the dual space of LP is LP prime, okay? If P is, yes, if P is not infinity, okay? If P is not infinity, the dual space of LP will be LP prime. This is called sometimes the Rees representation theorem. Okay, so we are going to get there. But before we get there, let's just build up a little bit on our theory of LP. I want to discuss to you, so this is the point of today. So I want to discuss to you a little bit about this so-called distribution function. So there is so if you give me a generic function f, okay, one way to give f some certain measure is to consider the level sets. So let's take lambda to be a number bigger or equal than 0, and you consider the level sets called E lambda. So these are going to be the points x in your domain, omega, such that, let's just take here modulus of f of x is bigger than lambda. Okay. So these are the points where the value of your function, let's put the absolute value here, but you could consider without if you wanted, is bigger than lambda. So the set of, if lambda is 10, so this is the set of points where f of f is bigger than 10. If this is 100, the set of points where f of f is bigger than 100. You see, these sets cannot be very big. If your function has some LP norm finite, for example, so if the integral of f to the p, yes, it's going to be a finite number, so you cannot have the set where the function is large to be also very large. Okay? So there is a way, sometimes this is called the distribution function of the modulus of f. There is a way to relate some objects appearing in the theory of LP spaces to the distribution function. I'll put perhaps to you as an exercise that this actually, when you define, so this has a few properties. That's obviously a non-increasing function. Okay, so if you take lambda 1 smaller than lambda 2, the measure this function, the graph of this function should look like this. Right? The larger the lambda you take, the smaller the set where f is bigger than lambda is. Okay? So it's a non-increasing function, and moreover, it is a right continuous function. If you just put the bigger here, not bigger or equal, if you just put bigger here, this is going to be. Hmm?
What does the height?
What does?
The height of this function.
Oh, I'm sorry. Yes, you're absolutely right. If I call E lambda, so I'm thinking about the measure of E lambda. Okay? Okay, thank you very much. So the measure of the set E lambda, the measure of this set, is a non-increasing function. It's right continuous. So you may have points where it breaks, and then here it continues. It's continuous from the right. This means that if you take minus this function, so minus the measure of these guys, this will be a non-decreasing function which is right continuous. So you have seen in one of the exercises that I posed to you to read that it actually defines a measure on the real line called the Lebesgue-Stieltjes measure. To every function that is right continuous and non-decreasing, you can associate a measure to it by measuring the intervals. It's just the difference between the points. So the Lebesgue measure just arrives when you consider the function f of x equals to x. But you can consider any non-decreasing function and define a measure out of it. This was one of the exercises that I posed to you on the homework number 2. But let's not talk too much about this now. I might pose some problems for you to think about regarding the distribution function here as a measure. So for now, let's just take a look at 2 facts. I just wanted to present to you 2 facts concerning these sets. The first one is called Chebyshev's inequality. You write Chebyshev's like this. And this is the following. Well, there is a way to measure the measure of these sets in terms of the LP norm. Okay? You just start. Let's assume for simplicity that we are in the case p less than infinity. Okay? So your LP norm of f to the p power will be the integral of f of x to the p d mu. Now, if I integrate over the whole domain, this is definitely bigger or equal than the integral over this set, which I call E lambda. Okay, that's clear. Now, on the set E lambda, my function is bigger than lambda. So this is bigger or equal than the integral over E lambda of f is bigger than lambda, or absolute value of f is bigger than lambda, so lambda to the p d mu. Now, this is just a constant, comes out of the integral. And the integral of the function 1 over the set E lambda is just a measure of the set. So you really have it here, lambda to the p times the measure of the set E lambda. Hence, you have generated an inequality. So this whole thing implies, if you just move this lambda to the p to the other side, you get that the measure of the set E lambda, whereas the set of f is bigger than lambda, less than or equal than LP norm to the p over lambda to the p. Okay? So the measure of, sometimes we call this the super level sets. Measure of the super level set associated to lambda, measure of the points where modulus of f is bigger than lambda, has to be, cannot be so big. It has to be always smaller than the LP norm to the p divided by lambda to the p. So you see here, when you send lambda to infinity, this side here will go to 0. Okay? Which makes sense because this number is finite. This is just a way to quantify. So keep this in mind. This is called Chebyshev's inequality. All right. Now, there is a space of functions. You can just look at this inequality and you can adventure yourself into spaces of functions that have a somewhat similar property. Okay? And sometimes it's convenient to use this space that we call, let's just say 1 less than p less than infinity again. We are in this case. And let's say we define this space that we call LP, and we're going to put a weak here, LP weak. Okay? This is the space of measurable functions. Again, identified almost everywhere. Okay? Identified almost everywhere, such that space of measurable functions f, identified almost everywhere, such that there exists a constant c, let's say bigger than 0, such that the measure of the set where f is bigger than lambda is less than or equal than c lambda to the p for all lambda bigger than 0. Okay? So I'm going to call this space LP weak is the space of measurable functions f such that there exists a constant c, which might be a constant depending on f, that's fine. But this constant c is such that the measure of the super level set is less than or equal than c lambda to the p for all lambda bigger than 0. So this constant c may depend on f, but of course it cannot depend on lambda. What we have seen here is just the statement that any function in LP verifies this property. Any function in LP verifies this property with this constant c being chosen as the LP norm of f to the p power. So, in other words, the space LP is contained in this space LP weak. This is what Chebyshev's inequality tells us. Another trivial thing is that this space LP weak is also a vector space. Right? You can take two functions f and g, and you can add them up. So the set where f plus g is bigger than lambda, you can use an inequality like this to say where f plus g is bigger than lambda, that's because f is bigger than lambda over 2, or g is bigger than lambda over 2. So you can use something like this to conclude that if f and g verify a bound like this with some c, then f plus g will verify a bound potentially with a different c. That's fine. Okay? And obviously, if you multiply your constant f by 100, you can just multiply your function c here by 100, and you're fine the same way. So this is really a vector space as well. Now, I'm not saying that this is a normed vector space, but this is a vector space too. And my question to you is that this is in fact something that contains LP, but it's not equal. So in fact, LP is contained, but it's different than LP weak. Okay? And there's the prototype of functions. Do you remember, can you tell me a function that would belong to this space but would not belong to this one? Can you think of a function? This is actually one of the very, nice examples that you should have in mind of integration at 0 and integration at infinity. So if there are a few things that you have to take from this course, okay? And one of these few things is that you have to leave this class knowing when a function integrates at the origin. Suppose you are in RD, you are in the Euclidean d-dimensional space. You have to know when a function integrates at the origin and when a function integrates at infinity. Okay? So let's discuss about this for 5 minutes, because this may be a source of lots of examples, nice examples for you. So, for example, if you are in dimension d equals 1, dimension d equals 1. So I want to look at power functions, right? I want to look at the functions that like x to a power. Okay, x to a power. When is the function x to a power integrable near the origin? So when is my function? So if alpha is bigger than 0, so this is my point. So if alpha is bigger than 0, the function is actually continuous at the origin, okay? So this is 0. So if alpha is bigger than 0, your function is just continuous at the origin and gives you a value 1, right? I mean, if you want. So a function that is continuous up to the origin is obviously integrable. The thing is, the interesting thing starts when alpha starts to get negative. So if you take the function, say 1 over x, is this function 1 over x integrable near 0? It's not. But how about the function 1 over square root x? Is this function integrable near 0? And this function is, right? You can just integrate. Let's integrate from 0 to 1, x to the minus a half. You can just use what you know. So the integral of x to the minus a half is equals to x to the 1/2 divided by 1/2 from 0 to 1. This is actually gives you 1. 1/2. Okay? You can just use integration. So you can integrate this function as long as, but if your exponent is x to the minus 1, then you are doomed, because the integral of x to the minus 1 is log, right? Log x from 0 to 1, and log at 0 blows up. So this is infinity. Okay? So if you are working with the power functions, it's good to know that this function integrates at the origin. Okay? So this function here. So I want to say this x to the alpha. So the integral, let's say from 0 to 1 of x to the alpha, the x is, this is going to be finite for any alpha which is bigger than minus 1. And this is going to be infinity if alpha is less than or equal to minus 1. Okay? How about at infinity? How about the integral from 1 to infinity of x to the alpha? Suppose you are in one dimension. When is this going to be integrable at infinity? Of course, you don't want alpha to be bigger than 0, because if your alpha is bigger than 0, your function will actually increase. This is obviously not going to be integrable near infinity. So you're really talking about negative alphas. But for example, this function 1 over square root x integrates at the origin, but does not integrate at infinity. To be integrable at infinity, the function 1 over x fails to integrate at infinity as well. If you integrate 1 over x from 1 to infinity, you get, again, log x from 1 to infinity, and log blows up. But then if you get 1 over x squared, and then this you are okay, right? You have always learned that the sum of the inverses of the squares converges, right? And this is because of this phenomenon. So whenever you are integrating a power, x to the alpha, from 1 to infinity, so now you want to integrate at infinity, you want the function to have a certain strong decay. As long, this will be finite if your alpha is less than -1. And this will be infinity for any other alpha which is bigger or equal than -1. Okay? This -1 that appears here is just the dimension. So if you are working in dimension, any dimension d bigger or equal than 1, and the function x to the alpha, so now if you are working in really with radial functions, you want to know when this thing integrates. Okay, so the integral from 0 to 1 of x to the alpha, or let's say in the ball of radius 1, of x to the alpha dx, this will be finite near the origin if alpha is bigger than -d. Here was alpha bigger than -1. But if you are in dimension d, it's going to be finite if alpha is bigger than -d. And it's going to be infinity if alpha is less than or equal than -d. This is a simple change of variable. You just use polar coordinates, and you come back to this case. So the one-dimensional case actually does everything for you. And again, the same thing at infinity. If you want your function to integrate x to the alpha dx outside the ball, outside the unit ball, you'd better ask for your function to have some strong decay at infinity. So this will be finite if and only if your exponent is less than -d. So it has to decay at least like 1 over x to the d plus some epsilon. Okay? And otherwise, it's going to be infinity for any alpha bigger or equal than -d. Okay? You see, so this is something that you should always keep in mind. When a power of x integrates near 0 and near infinity, okay? So it integrates near 0 if it's x to the alpha, and this alpha is at least -d. Then you're okay to integrate at 0. And it integrates at infinity if this alpha is less than -d. Okay? I'm writing here with x to the alpha. Of course, you can write it with 1 over x to the beta if you prefer to put the x in the denominator. That's fine too. Just rewrite this as you wish. Okay? But my point is, this function here is kind of a very strange and very limiting case. So this, if you take this function in Rd, f of x being 1 over x to the d, right? This is the x to the -d in that case. 1 over x to the d. This is a function which does not integrate near the origin and does not integrate near infinity. But it almost does, right? So near the origin, you would like to have something, it could not be 1 over x to the d, but it would have to be something slightly close. And at infinity, you're almost there as well. So it fails by just a little bit to integrate near the origin and at infinity. Okay, so this is not really in L1 of RD. This is not a function which is integrable in RD because it does not integrate in the origin, does not integrate at infinity. But then, let's take a look at the set. Let's take a look at the set that we call E lambda. This is the set of points x such that f of x, 1 over x to the d, is bigger than lambda. Well, then this is the set of point x where I move to the other side. So x will be less than, x to the d is less than 1 over lambda. So they say 1 over lambda to 1 over d. So in other words, it's just the ball, the set of, because this function looks like this, right? So the set of points where my function is bigger than lambda is a ball. So if I put lambda here, this is this ball, the set of points where my function is bigger than a certain lambda. It's a ball near the origin. It's a ball of radius 1 over lambda to the 1 over d. Now, what's the measure? What's the Lebesgue measure of this ball? Lebesgue measure of E lambda is the Lebesgue measure of the ball of radius 1 over lambda to the d. And the Lebesgue measure of a ball of radius r in RD is a certain constant, the radius to the r. I don't need to know what the constant is. It's just a constant times the radius to the d. Okay? Which is just a constant, maybe C prime, a constant here, and then lambda to the over lambda. So we have lambda to the 1 over d, which is the radius, to the d. So it's just lambda. So you see, the measure of this ball, the measure of the set where my function f is bigger than lambda, is equal to c over lambda for some constant c. That depends just on the dimension. And there you have it. So you have a function. I constructed when p is 1. You have a function such that the measure of the super level sets is actually c over lambda. And this function is not in L1. So this function, but this function here belongs to L1 weak. Okay? Mm-hmm. Yeah. L1 weak. Yeah, this is not unique. This is just, to me, the simplest example, and it also teaches you. So I should ask you, and whenever someone asks you when the power of x integrates near the origin or near infinity in RD, this is something you should know. Also, if you want this thing to, okay, we constructed an example in L1. We can also construct an example in LP trivially by just, so in LP, you would just consider 1 over x to the d over p. This is the function. If you want to consider in LP, you divide by p here because when you want to take the norm, you will raise this function to the p, and then you get to the previous scenario. Okay. So this is a function that does not belong to LP because when you raise to p, it does not integrate, but it belongs to LP weak. And the verification is the same as here. Okay? Okay, so this is a good point about Chebyshev's inequality and these examples of integrating near infinity and near zero, okay? So have this always in your mind. You would be surprised how many people don't know, don't know these things fluently. This is kind of very basic. Okay. Now, effect number 2 fact number 2 about the distribution function and the measure of the super-level sets is that you can relate it to the LP norm sometimes in a useful way. Okay, so relating to the LP norm. Let me do a computation for you here. See, so look, what's the LP norm of a function f raised to the p power? This is just the integral of f of x to the p d mu of x in your set omega, right? Now let me write this f of x to the p as follows. I'm going to write this f of x to the p as the integral from 0 to f of x. So of the function p times t to the p minus 1 dt. So I'm just using here a fundamental theorem of calculus, okay? P t to the p minus 1 is the derivative of t to the p. So by the fundamental theorem of calculus, the integral from 0 to this number of the function of this function is t to the p, f of x to the p minus 0 to the p. It's just f of x to the p. Okay? So this is just a basic fundamental theorem of calculus here. So this is just this, the mu of x. Now you can write this as the integral in omega, and then the integral from 0 to infinity. Here you have p t to the p minus 1. And what you really have here, so I'm changing the integral from 0 to infinity, because this was an integral from 0 to f. So this is really the integration in t takes place in the characteristic function of the set, characteristic function of the set where f of x is where t loses to f of x. Okay, for a fixed x, t. So if you want, you can write it like this. dt d mu of x. So I'm just rewriting the inner integral. Instead of taking from 0 to this number, if x is fixed, I'm just taking the characteristic function on t, where t is less than f of x. That's fine. Now there's a moment where, this is a moment where we can use Fubini's theorem. And if you're paying attention to this course, you should raise your hand, but professor, we haven't yet proved Fubini's theorem. Yeah, so I'm taking a little bit of a license here. This is something we haven't proved yet. We should prove by the end of next week. But you know, Fubini's theorem is the theorem that you can have two integrals, you can interchange them. Okay? So you can interchange them as long as one of the two things happens. So if the double integral of the modulus is finite, or if whatever is inside is non-negative. So if you're integrating, if you have multiple integrals and whatever is inside is non-negative and measurable, of course, you can always interchange things. And this is the case here. You're kind of you're integrating all non-negative things. So we're going to prove that we can switch these. And when we switch, look at what happens. The integral from 0 to infinity will come out. The integral in t will be p t to the p t minus 1. And then you have the integral in omega of this function here. Mu, and then dt. Okay, but this is the measure of the superlevel set. If you now fix t, and you look at the sets where f of x is bigger than t, this is the integral from 0 to infinity, p t p minus 1 times the measure of the set where f is bigger than t. Okay, so this is what you have proved. There's a way to write the LP norm as an integral of a certain function times this, what we call the distribution function. Okay? Again, I owe you Fubini's theorem to make this work, but we'll get there. But just for now, when you look at this formula, you see something nice going on. So from this expression, if two functions, f and g, have the same super level sets, they must have the same LP norm. See, if this quantity is equal for f and g, then they must have the same LP norm. Okay? So if somehow you can rearrange the mass, if your function f is floating around, but you can rearrange the mass of the function and make a new function such that the level sets are the same, the measure of the super level sets are the same, then you won't have changed the LP norm because of this expression here. Okay? So as a corollary of this formula, as I'm saying, if the measure of the set where f is bigger than t is equal to the measure of the set where g is bigger than t for all t bigger than 0, this implies that the LP norm of f is going to be equal to the LP norm of this function g. Okay? This little trick that we did here with the function t to the p, okay, you can do with any other continuous function. Okay? So I'll put you as an exercise, maybe, to verify this following. If you're given a function phi, let's say a continuous function, such that phi composed with f, phi of f, say belongs to L1 of omega, then so you would have the integral in omega of phi of f of x, the mu being, I guess, minus the integral from minus infinity to infinity of phi of t. D, then you would have to call, we would have to call this lambda is a bad choice, but let's call nu of lambda being this measure of the set where f is bigger than lambda. It's not exactly this thing, so but nu. Okay, so nu. Nu is the measure associated to the right continuous function minus mu, minus the measure of where f is bigger than lambda. Just call it this. This is the measure given by the distribution function. So in some sense, this is just what we did, So this is just an application of this when this function phi of t is t to the p. Check out. I mean, I might outline in an exercise for you how to prove this thing. Again, this is the measure of, here I'm not putting the absolute value, but that's fine. So if you have a distribution function, the measure of where f is bigger than lambda, this is a decreasing function, non-increasing function. So if you take minus, this is going to be an increasing function, non-decreasing function, which is right continuous. It generates a measure called the Lebesgue-Stieltjes measure, which I'm calling nu here. So I'm integrating this continuous function with respect to this measure here. Okay. Or maybe I should call it the same, minus the, no, that's fine. Let's just call it that. Just call it that. if you call it nu of t, nu of lambda equals to this. Sorry? Why not the modulus? I mean, you can put it for any f here. This statement is more general. If you want to put modulus of f, I mean, you just change the function. I mean, instead of putting the function f here, you can put the function modulus of f if you want. That's fine, too. The function modulus of f is a function. I'm saying that this holds for any function. Not for this general statement, no. Okay. But we can talk a little bit more about this later on. Let's see. Okay, so let's perhaps okay, no, this I have to, since I put the minus here in front, if I want to put the minus, well, no, take the minus here because I'm putting a minus here. Okay, so just define this nu of lambda being this thing, and here you have a minus. That's fine. Or if you prefer, just take this as minus here, and then remove this minus. Okay. Now this is really a right continuous non-decreasing function. You can construct the Lebesgue-Stieltjes measure associated to it, and you have this expression. Okay. Let's see. I would like to finish the class today, talk to you guys a little bit about Jensen's inequality. Okay? So don't forget this discussion about how the distribution function comes into play, Chebyshev's inequality, LP space, LP weak, and this relation between the norm and the distribution function, even this more general statement that we're going to prove sometime soon. Or maybe you will prove in an exercise in your homework. Let's move a little bit to the discussion to treat objects that look like this, but in a very clever way. So this is called Jensen's inequality. So maybe some of you know from before, from your high school years, you might have gotten to know these inequalities before in your life. You know, the arithmetic geometric mean inequality, maybe even Holder's inequality. Of course, you have Cauchy-Schwarz inequality, which is a particular case of Holder's inequality, for example. Some of you may have heard about Jensen's inequality, maybe in the context of sequences. Instead of working with LP spaces, it's more common for when you're in high school to learn these inequalities for sequences of numbers, right? This is how I learned, for example. I used to participate in this math Olympiad, so there was a bunch of nice inequalities that one can prove. Yeah, so all of this, I mean, we could spend the whole class just doing problems about inequalities in mathematics. I mean, yeah, exactly. Yeah. So this is one of my favorite inequalities, Jensen's inequality. And really, as in Holder's inequality or as in Minkowski's inequality, we can put them in the context of measure theory, where you have integrals over spaces. And these integrals might be sums if you're just working with the counting measure on the natural numbers. So this is actually a generalization of some things that you might have learned in high school for sequences. And it goes as follows. So let's just see. So a function, let's say a function. So a function phi on an interval a, b, say taking values in R, is convex Okay, so here I'm taking an interval AB contained in the real line, okay? I'm taking an open interval AB contained in the real line. You may have A, that's okay to have A equals minus infinity and or B equals infinity. So you may have open-ended intervals, that's fine. So just take an open interval in the real line. A function phi from this interval, let's say taking real values, is said to be convex if the following property holds, if phi of, let's say, lambda x plus 1 minus lambda y loses to lambda phi of x plus 1 minus lambda phi of y for any pair of points x and y in your interval AB and lambda between 0 and 1. Okay, so this for me is going to be the definition of convexity. As he was mentioning, if you have a function which has two derivatives, is C2, and the second derivative is bigger or equal than 0, then the function is convex. But this function doesn't have to have two derivatives. You can just start with in principle, yes, it will be continuous from the definition, but in principle, you don't even know that it's continuous, you know? This is something you can prove, that if it verifies this inequality, then it's a continuous function. Yes. Okay, so this is the definition. Just give me a function from this interval such that it verifies this property. So whenever you have points x and y, you take this linear combination, lambda x plus 1 minus lambda y. So this is a point in between them, because lambda is between 0 and 1. So it's a point in between 0 and y and x and y. So the value of the function at this point has to lose to this particular quantity, lambda phi of x, and this other way, 1 minus lambda phi of y. So there are several equivalent ways of stating this. Okay, so this is one way, star. So 2, this is an equivalent way, would be to say that, well, if you draw the graph of your function, whenever you have the point x, phi of x, y, phi of y, so you draw the line and you get the point here t, in between them, the value of the function at the point t has to be below the line that connects the point x phi of x to the point y phi of y. So the point phi of t has to be here. So an equivalent way would be to say that, let's say, if t belongs to an interval x, y, then the point t phi of t lies below the line connecting the points x phi of x and y phi of y. So this is equivalent to 1. And you really, if you write down the equations of the line, another equivalent way to say the same thing is the following. So if you have your A is the endpoint of the interval is less than u, less than t, less than s, less than b. So for any 3 points u, t, and s in your graph, so let's suppose here you have your u, you have your s, you have the values of the two, you have the line connecting them, and you have your function. So the point t, phi of t will be less than the value connecting these two guys. So another way of saying this is that this slope here loses to this other slope. Another way, in other words, phi of t minus phi of u over t minus u. This first slope should lose to this second slope, phi of s minus phi of t over s minus t. So my claim to you is for you to verify that these three ways, these are three ways of saying the same thing. Okay? These are three ways of saying the same thing. Okay. The second exercise for you is to actually verify that a convex function is continuous. Yes. So if a function is convex, it is continuous. Okay? You can kind of take a look from the graph here. I mean, if you have a point, let's just think about it a little bit. If you are in this situation that you have a point here and a point here, and you want to show it's continuous on a point, say, right here, you know that this point lies below the line. You know the point lies below the line. So you kind of know that if you draw this line, and if you draw this line, so the graph of your function to the right of your point, P, will have to be trapped in this region. And the graph of your function to the left of this point here will have to be trapped in this region here between two lines. Okay? So as you approach this point, since your graph of the function will need to be trapped between these two slopes, and here trapped between these two slopes, you get that the graph has no other option than to converge to your point. Okay? So just think about it. I mean, you can think in a different way, but this is the graphical way that I think about it a little bit. Yes, a convex function is... To prove that the convex function with these definitions is continuous, you don't have to use any big result. It's just really a matter of using the definition. Of course, if you are solving our homework problems and you end up wanting to use a big result to prove any of the homework problems, you can do that. That's fine. I'm proposing to you the homework problems with the idea that you can solve with what we discussed. But if you find a solution that goes out and uses any theorem that we haven't seen, that's fine too. Just make sure that you learn that theorem, that you know how to use it, and that you add it to your pool of knowledge, okay? So let us state and prove Jensen's inequality. So theorem, and then we finish for today. Jensen's inequality. Let me state it properly, and then we will prove. You know. Okay, so let omega sigma mu be a measure space such that the measure of the whole space is 1. Okay? So this is actually a probability measure. So the measure of the space is 1. Let f be a function, be in L1, be an integrable function, be a real valued function. Let f be a real valued function such that, say, the values of f always fall between numbers a and b, okay, for all x in your domain omega. You may have, remember, a minus infinity or b plus infinity. That's fine. If your function, if phi is a function from a, b to r, is convex, then what you have is that p of the integral of f omega loses to the integral of phi of x. That's it. So in other words, the average of phis of f is bigger or equal than phi of the average of f, if you want to think it like this. If you think about the probability measure being an average of f. So this is your Jensen's inequality. Let's try to prove it. Proof. Really? So let's say the first thing to notice is that, okay, so let's call t this number, integral of f d mu over omega. So if f is always between a and b, and I put here strict inequalities, when you integrate f over this probability space, you get that this t is between a and b. Okay? Think about why. Because in principle, you could have t equals a, or you would have less than or equal to a, less than or equal to b here. But think about why it cannot be equal to a, or why it cannot be equal to b. And my claim to you is that if f of x is strictly less than b, I mean, for all x, so then it's going to be less than b minus 1 over n in a little set of positive measure for some n very large, and some little set of positive measure. And then this will make this integral be less than b. Same way you can prove that this integral is bigger than a. But anyway, so this is a number that we call t, and I want to use this inequality here. Okay? So this is going to be my t. So let's call this number 3. So you let's call beta be the supremum of the left-hand side of this inequality 3 star Okay, so these quantities, for all u less than t, this quantity always loses to this quantity on the right, for any s bigger than t. Okay, so just pick an s, fix this number on the right-hand side, and then for any u that you plug in here, this will lose to this number. So then you can take the sup over the left-hand side. Call it beta. Beta the supremum of the left-hand side of 3 over all, say, u less than t. Okay? Of course, since each of these numbers loses to phi of s minus phi of t over s minus t for any particular choice of s to the right of t, then the supremum over the left-hand side also loses to any of these numbers here. Okay? So then you have that beta loses to the right-hand side, phi of s minus phi of t over s minus t, I'm saying, for any s that is bigger than t. Okay? And now, I claim to you the following. I claim to you the following inequality. That phi of s is bigger or equal than phi of t plus beta s minus t. I claim that this holds for any s and t. Okay? Of course, if s is equal to t, you get 0 here, and you get phi of t equals to phi of t, so that's fine. Now, if s is bigger than t, what I'm saying is that phi of s minus phi of t over s minus t is bigger or equal than beta, which is fine, right here. Check. And if s is smaller than t, let's see, if s is smaller than t, I would move to this side. I would move beta t minus s, would lose to phi of t minus phi of s. This would be equivalent to saying that beta loses to phi of t minus phi of s over t minus s. For all s less than t, beta, no, I changed my sign. I didn't have to change my sign. For any s less than t, beta would have to be bigger or equal than this quantity, which is also fine because of the way I chose beta, right? I chose beta to be the supremum of these quantities here for a parameter u less than t. My parameter here I changed to s. Okay, so this is also fine. So you really have this inequality here with that beta chosen like this, and t being this guy, you have that phi of s is bigger than phi of t plus beta times s minus t for any s. Well, I'm sorry, t is fixed for any s. Okay? So now what we have to do, all we have to do is to integrate this thing here. Okay, we integrate on s. So let's call this big star. And now we integrate this big star. When we integrate, what do we get? Integral of phi of s. Let's say I'm integrating on omega, d mu of s. Not this, I'm sorry. Not yet this. Not calling this star. So what I want now is to, so this thing implies, now I put s as any f of x. So I have phi of f of x bigger or equal than phi of t plus beta f of x minus t. Okay, and this holds for any x in your domain. This is what you call star. And now what you do is you integrate star over your domain. So when you integrate this over your domain, what you get is the integral over omega of phi of f of x d mu of x is bigger or equal than phi of t. So phi of t was just the integral of f mu over omega plus, and then here you get beta times the integral of these guys. So you get the integral of f in omega, integral of f minus t. Okay? So now just observe that this is the integral of the function f of x minus t. T is fixed. Okay? So this is the integral of f minus the integral of t. T is a fixed number. So t comes out of the integral. So minus t times the integral of the function 1. The integral of the function 1 over omega is just the measure of omega that we agreed that it's 1. So this is a probability measure. Okay? So this number here is just 1. And the integral of f over omega, we agreed that the integral of f over omega was this number that we call t. So you really get here t minus t times 1. So this is the magic. This whole thing here is 0. And there you have your inequality. Integral of phi of f wins against phi of the integral of f. Okay? So this is just a clever way of applying the convexity here. But then the possibilities of using this inequality are really, really huge. Okay? I just put in your exercise just one very minor possibility, which is to apply and prove inequalities of the sort arithmetic mean bigger or equal than geometric mean with any weights. Okay. Before we depart today, let me perhaps mention, before we move our discussion from LP spaces to other things, let me briefly mention a little bit about dense classes in LP. Okay? So whenever you are working with LP spaces, sometimes if you're facing a problem and you want to prove a certain property for a function in LP, it's convenient, it might be useful to prove it for more special functions, more simpler functions, and then extend by some sort of denseness. You know? So it's good to know these dense classes in LP, because this might be helpful for you whenever working in your homework, but also in exercises in the future, in different courses here, not only in analysis, but PDEs. So the first thing that you should have in mind is whenever we talk about, remember what we discussed about simple functions. So simple functions, simple functions are dense in LP, 1 less than or equal than p less than or equal than infinity. What do I mean by dense? Well, meaning that given epsilon bigger than 0, so given a function f in LP and epsilon bigger than 0, you can find a function phi being a simple function such that the difference between f minus phi in the LP norm is less than epsilon. So this is what I mean by being dense. You know, if I give you a generic function in LP and I give you epsilon, I can find a simple function such that the distance of this simple function to f in the LP norm is less than or equal than this epsilon that you gave. So if you want to rephrase it, you can actually construct a sequence of simple functions that converges to your f in the LP norm. That's another way of saying the same thing, you know? But the point is, sometimes, whenever you want to prove a statement for a general function in LP, it suffices for you to consider simple functions. Even if the statement that you're trying to prove is something linear, you don't even have to consider simple functions. You just have to consider the characteristic function of one set, because then you'll be able to extend for simple functions, and by density, you'll be able to extend it for LP. Okay, so these sort of simplifications are very, very important. Now, we have already seen this, right? Remember, for example, in the proof of the monotone convergence theorem, that we can actually construct a sequence of simple functions. Recall that we can actually construct a sequence of simple functions such that, you know, that they would converge to your f. These simple functions are monotonically increasing to your f. Remember that we just took the graph of f and we just split the image, right? We will split the image here in some intervals, and then take these functions splitting the image. And then at each step, we would go up our height and actually subdivide each interval in two. So this splitting was a dyadic splitting. So this is in the proof before the monotone convergence theorem. So if p is equal to infinity, if your function is in L infinity, then this means that this function is bounded. You can actually just split your interval from 0 to whatever bound is into as many pieces as you want, and you can find simple functions whose distance to your original function is smaller than this gap. So the statement pretty much follows from this. I'm not saying that the sets here have to have a finite measure, okay? Simple function is a linear combination of measurable sets, of characteristic functions of measurable sets, but the measure of the sets could be infinity. That's fine. Now, if you are in LP, then you really have to use you can use the monotone convergence theorem that we used in the, let's say, with the positive part of f and the negative part of f. And then you use the triangle inequality here, so you can really just work with the positive part of f. And by monotone convergence, so this integral of this sequence phi k to the p will converge to f to the p. So this is a monotone thing, you know? Or if, in other words, so this, so phi k to the p will lose to f to the p. So you can actually use dominated convergence theorem, dominated convergence or monotone convergence, whatever you want here, just to guarantee that the integral of f minus this phi k's and the p norm, okay, since this is dominated by 2 times f to the p, so this is a function in LP, so you can use dominated convergence to see that this goes to 0, because phi k goes to f pointwise. Okay? So this is really something that we have already done. So simple functions are dense in LP for any p in any measure space. Okay? So now I want to just finish the class today to talk a little bit about what do you get more when you are working on the Euclidean space. So now we move our discussion to RD, okay? So on RD, with the Lebesgue measure, you also have this class of step functions. Step functions are finite linear combinations of characteristic functions of cubes, okay? So step functions, they are dense in LP of omega. Let's say omega is a subdomain of RD, an open set of RD, for 1 less than or equal than p less than infinity. Okay? I'm not including infinity, because I might take a function which is infinity, let's say a function that's identically 1. You cannot approximate this function by a step function, because a step function is something that's bounded. I mean, it has a bounded support. Okay, so it's clearly not dense in L infinity. But it is dense in LP for any other p less than infinity. How do you do the construction? Well, you can start with your function f in LP. You can approximate by a simple function like this. And then you can take your simple function, since it's in LP, you can truncate the support. Okay, so I can approximate by my simple function, and then I can approximate by my simple function intersection the characteristic function of a huge ball. And then this one, which is another, simple function, but now with the sets being of bounded sets, we have seen that we can approximate these by step functions. Remember that any measurable set, which is bounded, can be approximated by a finite and disjoint union of cubes. We have seen this statement in the regularity of the Lebesgue measure. Okay? So therefore, this is how you do it. You start with your function f. You approximate, if you are in RD, you approximate it with a simple function in LP. Since this is in LP, you can actually truncate your function with a ball of huge radius, and the tail will have small LP norm. So you can actually approximate by a simple function where the functions involved the measurable sets involved are actually bounded. And then each measurable and bounded set you can approximate by a finite union of cubes. And then you do this and you get a step function. Okay? Number 3, continuous functions. Continuous functions, or even continuous functions of compact support in RD. These are also dense if 1 is less than or equal than p less than infinity. So continuous functions are dense in LP for p bigger or equal than 1, but not infinity. If p is not infinity, how do you do? Well, we have seen that if I'm working in RD, I can get a step function that is very close to my f, right? But if I can get a step function, then I've seen that I can take a function of a cube and just modify it a little bit to make it continuous. You just take your cube and just take a characteristic function of a cube and just put a line here to make it continuous, and you're paying a very little price. That's fine. But this way you can take your cube and just modify it a little bit, even linearly, just to make it continuous, and you pay a very little price. You still get a function which is close to your original function, f. Okay? What if p is equal to infinity? Can I approximate a function which is L infinity with a continuous function? No, you cannot do this. And a basic example would be the signum function. So if you take a function which is like this in R, just 1 and minus 1, and has a jump, you can never approximate this function in the L infinity norm by a continuous function. Okay, because your continuous function will have to make a jump, and then at a point here, it will be very far, or even at a point there. Okay, so this is not dense in LP. And again, what I told you about continuous functions approximating step functions, if you have a step function, you have just finite number of cubes, you take each cube and you just adjust it linear to make it a continuous function. This will actually make a continuous function of compact support. So you can even say that continuous functions of compact support are dense in LP of RD for p bigger or equal than 1 and less than infinity. And finally, you can even say that continuous functions, C-infinity functions of compact support in RD, they are also dense in LP. Weierstrass theorem, well, this is slightly different, right? Because Weierstrass theorem says that polynomials would be dense in the continuous functions if you're working in a compact set. Yes, I mean, I can see that. I can see that going on, but yeah. I mean, there are many, dense classes that you can take. You choose whatever is more convenient for you. I'm just going to finish here. So, C-infinity of compact support, these functions here, these are the functions that are infinitely differentiable and that have compact support to this. This will also be dense in LP. Also, if P is not infinity, because this is also a counterexample, but this is a subclass of this. We shall go back maybe in a few lectures to actually prove this. This is, we would have to prove this. I mean, 1, 2, and 3. I let you to fill in the details and take a look at this. Please, think about this because this is very important. So take a look at home. Think about these dense classes. Convince yourselves that these classes of functions are dense in LP in each of the cases. We will come back to this point number 4 in a few lectures down the road. But this is, I purposely put maybe 2 or 3 exercises in your homework now that it would be very much easier for you if you apply one of these things. So if you want to prove a statement for a function in L1, especially if it's a linear statement, you just have to prove for step functions. Since your statement's linear, let me just prove for the characteristic function of 1 cube. If you are working in 1 dimension, you just have to prove for 1 interval, okay? So whatever you had to prove for L1 just reduces for you to prove for a function that is just the characteristic function of an interval. That's much easier. And then you argue by, okay, by linearity, if I prove for one interval, I prove for a step function. And by denseness, I can argue that I can prove for any L1 function, okay? So these sort of arguments should be in your playbook, okay? Work on this, solve a couple of exercises, get used to these arguments that you have to use the denseness to prove your question. If you start with a very crazy function in the beginning, that's much harder to approach the problems. Okay, let's finish our discussion here today about LP. I hope you guys enjoyed. The plan for next lecture is to do a little bit of Hilbert spaces, because I want to prove that the Rees representation theorem for Hilbert spaces to then apply and study the Radon-Nikodym theorem of the decomposition of measures. So the plan for the next 2 or 3 classes would be to do a little bit of Hilbert spaces, Radon-Nikodym, and Fubini's theorem. And then we are going to have a week of break where you will do your midterm in the first week of November. Thank you, everyone. Have a good day today and tomorrow, and we get together again on Thursday. Bye-bye for you guys that are watching at home.